So essentially, the Detector ring goes like that, and you know what it does, right? We have protons, we have antiprotons, we accelerate them as much as we can, we make them collide. And then, in these bunches of particles that come, some particles with the antiproton will collide with the other ones in the proton, they will make a lot of things, but they will keep on colliding. So you can imagine, the Detector ring actually goes parallel in this direction. It's about 30 feet underground and about 50 feet over there. And you can imagine this actually being in the beam pipe. And if you see in there, this little cross-section in here, that's the beam pipe. That's where protons and antiprotons come from in different positions, from different directions, and collide. And the very first thing we put very next to the interaction point, to the point where things collide, is the silicon detector. So this is a mock-up, obviously. It was one of the first, let's say, mock-up of the silicon detector that were built to see how everything will fit. This is just 1/3 of it. Then after this we have another barrel like this one in here and another one over here. So the whole thing is like this. And then in addition of that we have more silicon, and the total length of the silicon is about 2 meters at the model. So today I think the lecture was perfectly explaining how we use the silicon detector. And this is a piece of silicon. It's very down there. So you don't see it now, but I'll pass it around. But this is just a wafer of silica all along, and we have aluminum strips on the top, and they go all the way like that. So these guys go to here, and these guys go to here, and we can tell when a particle passes through which strip fired, which particular strip was the one that collected some charge. So we can tell whether the position was in there or in there or in there, just by looking at what particular strip fired. And then what we do, you can pass this around, you can try and see it. It's very hard to see. They are very, very close together, these aluminum strips. And that's another one here. This is a little different because in that guy, it's only strip this way. Right? So if you get a hit, you don't know whether the hit passed in the same strip, it was in this position or in this position. So you don't really know what coordinate C the charge particle passed through. This one is a little different. This one we have strips like this, and we also have strips that go like that. So that way we can tell when a particle passes that this strip and this strip over here in orthogonal coordinates fire, and therefore we say, the particle passed exactly this point. So this is what we call a 90-degree strip. Let's see the position like that. You can pass it around slowly. So how do we use this to actually reconstruct what happened in the collision? If you look at this on the side, we have several layers, and we put the silicium, many of those, a lot of those, in cylindrical layers. We create one layer, then we put a second layer, then we put a third one, and so up to 7 layers. So if you look at this on the side, you can see all some of the silicium inside. You see, these are all what we put the silicium. Some of them are empty because it's a mock-up. And then you have to expand this and imagine, this on this side. And so what happens when you get a collision? You get a collision roughly in the center, you get a lot of particles coming out. When you look at the whole thing together, from the side, you can see what points the track was made, and then we have a very sophisticated algorithm that essentially tries to reconstruct that into a track and to say, one particle passed all over here, leaving all these hits around in the silicon detector. And so this algorithm is very sophisticated. We need to reconstruct all sorts of tracks in one single collision. We have a lot of them, so we need to be able to reconstruct all of them. And it takes a significant portion of time to actually do it. So this is the silicon detector. It's very close to the interaction point, and it gives you a very small track. It tells you the silicium is only this big, so it tells you a track only about this size. But it's very precise because it's close to the interaction point. You can tell very well where the particle is coming from. Is it really coming from the proton and the proton beam, or is it coming a little offside? Because if it's coming offside, it's because something was producing the interaction point, moved, and then decayed, producing all the particles. So these things allows you to tell this big difference, and we're talking about here micrometers, 20 micrometers. So a micrometer is 10 to the minus 6 meters.
Do the silicone layers, like an air conditioner filter, over time get dirty or degraded or wear out?
So what happens with the silicon detector is that all these collisions also result in radiation. This is very high radiation. This thing has to withstand the radiation. And it's very hard. This is the second time we use a silicon in.
How long do they last?
So we don't measure in terms of time, we measure in terms of radiation. But let's say we replace it every 5 years. Now the accelerator is doing so well that our silicon is degrading too much. So it's, I'm the project leader of the silicon. So it takes a lot of effort to actually make the silicon work up to this condition. You need to play all sorts of things. You need to increase, for example, the voltage continuously. You need to do some very tricky things. And the worst part is you don't get access to it. It's barely underneath everything else. Right, that's about silicon. And so imagine the silicon this size, and then on top of it, outside the silicon, we put that big chamber over there. So let's move over. So we have the silicon right outside the interaction point, and this goes outside the silicon. So the silicon has actually been inserted into this big drift chamber. So, by the way, the insertion of the silicon in here was a major task. The clearance between the silicon and this thing was 0.5 millimeter, and they had to put these two big things weighing a lot into this without smashing it. Right? I myself wonder how they did it. So this is again outside the silicon, and it has the exact same idea of the silicon. In the collision point you get a lot of tracks. Some of them are measuring the silicon, and then outside you want to measure with a much more lever arm these tracks. So you're able to tell even more accurately where they came from exactly, and to measure the properties there. How is this built? Well, it's very simple. It's really just one continuous chamber that's filled with gas and has a lot of wires. So all these little holes you see here on the side connect to a wire that goes all the way through in there. And the mechanism by which this detects particles was probably explained today by myself. This is simply a wire chamber, what we call a wire chamber. It has the gas. Any charged particle traveling through it is going to ionize the gas. And these ions will travel to the different wires. And in the same way we have with the silicons, whenever one particle passes close to a wire, it's going to leave some charge on the wire, and we're going to detect the charge in here. And so we have a lot of wires like this. Again, I think it's 7 layers. And same as before, if you look from this on the side, you are able to, just by looking at the wires that show some charge, you will be able to tell, oh, there was a particle going this way or a particle going that way. However, same with the silicon, you are not able, if the wires were perfectly parallel to the beam pipe, you were not able to tell whether the charge was collected here or in there. And we want to know that information. We want to know that. So what they did was bring a little trick. Some of the layers go straight, some of the layers go straight, the wires go straight. But there are some layers, some wires that imagine there are wires connecting my fingers from each finger to each finger, right? They twisted it a bit. So then there was a small angle. And that small angle, in addition to the other layers that are straight, allows you to tell the Z information in the Z coordinates. So when you look at this, and that's also with the lines and so you can do this. Some of the wires were straight and some are tilted. Can you see that? By looking at the reflection? Barely. Yeah, it's very hard to see. So to give you an idea, the reason we did this, a wire chamber and the other silicon, is because silicon was very expensive at the time. And building such a thing of silicon was just impossible. Imagine this has 30,000 channels. The silicon system has 750,000 channels. So it's much, much bigger in terms of channels. The future detectors that we already built, and they are at CERN, have actually this size of pure silicon. And that's an amazing number of channels, more than 10 million channels that you need to reconstruct, analyze everything online in 30 nanoseconds.
What are these wires?
What?
These ones silicone.
These are just regular wires, and they just look at the ions coming from the gas.
Like
that ionizes. Just come. What are they made of?
Oh, that's a good question.
I'm not sure. Whatever's cheapest.
Well,
Well, you know, this is already cheap.
Yeah.
So I doubt they use the cheapest material to do the wires. But alright, so let's come back here again.
Cost effective.
Oh yeah. So we have the silicon in there, right? And then we have this big thing. And if you had no magnetic field, all the particles coming out of the collision would just be straight lines, right? Nothing else, going in all the different directions. So outside this, we put a huge superconducting solenoid, and I'll show you the control room of the solenoid in a bit. And it's essentially outside this, what we call this drift chamber, and generates a huge magnetic field. So when the particles come out of this, they don't just go straight, they bend, like Marcel was showing you today. And depending what side they bend, you can tell whether it's a charged particle or a positively charged particle or a negatively charged particle. So then you have to imagine here outside a big solenoid. And then you have to imagine outside the solenoid, these particles go straight, they pass through the solenoid, they barely feel the solenoid, they pass through, and we lost them? No, we want to measure their energy. Because with this, we measure the momentum. So we want to measure what the energy of the particles is, and then we have the full momentum. So outside the solenoid that is in here, we have 48 of these guys. These are called calorimeters. The only thing these guys do is just measure the energy of a particle hitting it from underneath. So imagine 24 of these pieces surrounding this on this side, and then 24 on the other side. We have separated east and west. So let's go over here and see how these guys look. This is the commission. This was used here actually on 1995. Actually, this is the one that is covered the top part. It's covered here. Come on, guys. There's no hurry. Okay, so this again surrounds the solenoid that's outside that, and then particles will pass through the solenoid with everything in there, and will put it here. And this is essentially divided in two pieces: the electromagnetic calorimeter, the hadronic calorimeter. And Marcel was talking about that today. This part here is what we call electromagnetic calorimeter. This part from here up is what we call the hadronic calorimeter. They are both made in the same way. It's one layer of some material, very dense, either lead or iron, and one layer of scintillator. And then we repeat that. So you see all the different layers in here, right? Scintillator, lead, scintillator, lead, scintillator, lead, and so on. So when a particle goes in here, if it is an electron or a muon or something electromagnetic, it will produce a shower. And Marcel today had a very nice description of the shower. And it will produce a shower in here. And essentially what we do with this big piece of scintillator in here is just capture the light. Because the shower, all these different particles in the shower will produce telecom light. This light will come on the outside and it's connected by this big thing here. And then it's guided all the way up to a photomultiplier tube. And you've seen that today as well. So with this guy, by just looking at the output and the current this guy gives, it's telling you how much energy was deposited in this particular tower. Electrons and photons are typically absorbed in here. So they go in there and they die. Hadrons on their side, they will interact here very lightly, but they will interact with this material much more. And they will produce a very similar shower on this material. So that's also has to be larger, because the interaction of a hadron is completely different from the interaction of an electron or photon. And the reason for that, as I explained today, is that electrons and photons, they tend to interact with the electrons in the shell of the atom. Hadrons tend to interact with the nucleus. So that's the reason we use different materials, because this has a lot of electrons. has a very dense nucleus, which interacts very easily. And we do the same here. For each one of these scintillators, we have a fiber scintillator that is bent, and we collect all the charge, and all the charge goes into this photomultiplier. And we have two per tower. We call this a tower, and we have another one, so we can tell what position the particle hit, like if it hit in here, or if it hit in here. Am I going too fast? Okay. So we have 24 of them outside, and then outside all that, we have a muon chamber. So I'm not having... Yeah, let's go.
Oh, sorry.
So this is a little mock-up of the whole detector. This is the wire chamber that I was showing you earlier. Now you can see that the silicon in comparison to the whole detector is just nothing. This represents all the calorimeter wedges, like this one by one, surrounding the COP. And then outside that we have everything with steel. And the reason we use steel is because we want to detect muons. Muons go through this like nothing. They leave a track, of course, in the wire chamber. They pass through the calorimeter with only very little energy. And so we want to make sure they are muons. We want to make sure that it's not maybe a shower that was absorbing this detector. And for that we put steel. Because if something else that's not a muon will come through, will not pass the steel. A muon will. So we put a very thick wall of steel here. And then on top of that we put scintillators that just detect when some charge particle pass through. And if a charge particle pass through all this, it's got to be a muon. And then we also put these things in here. These essentially are wire chambers, but they have only 4 layers. So they are able to reconstruct a rough track. They are able to tell, if a particle passes like that, they are sort of able to tell what direction they came from. Yeah, there's nothing in there. So, but that's the way they work. And we surround the detector with those. The detector is fully surrounded by those. And by doing that, we essentially get this cube. Then we put more muon detectors in here. Yellow things in here, these are all muon detectors. They detect things passing out of the steel. And then if that wasn't enough, we surround the things with 100 tons pieces of steel. And we put scintillators in here and in here to compete with the side. So it's a huge detector. And to build it is even stunning. So let's go over here and show you what it was. What you see in there is a real-size picture of the detector. It's a $5,000 picture, really. It costs $5,000 just to print that out. So that's a real position in which the detector, the main components of the detector were built. Everything.
I'm just listening.
Everything was actually gathered in there, built in there. And these pieces on the floor were retracted, they were moved out of the way. And then the detector, once built, was rolled in inside, behind that orange door that you see over there.
Okay. So
28, yes.
okay. It's behind there.
Thank you. What?
It's behind there.
It's
Okay.
behind there.
Right. Wow.
And it's like that, and this is the orientation of the electron beam.
Okay.
So, and you should see, there are movies in which we fast-moving movies, in which you see how everything was built and put together and how the days roll in, but then things moves by inches towards its final position. It's fantastic. All the things that are in there. Oh, that's the name of all the people who helped at the time on building this thing. I'm not even there, so I wasn't even here at the time. Yeah, so what you see in there, you see in the picture something that you don't see behind. And above the lens, that's a cable tray. the orange thing in there, and you can see all the cables. Those are the cables that go through the detector to the control room. I'm going to go to the control room in a few minutes. But so the cable tray, you can see it contracted over there, right? It's contracted over there, you see it? And it used to be all the way up to here. So when that was moved, the cable tray was contracted. So let's see where the cables go to. Go back to the 9, right? Wow! Okay, let's fit 5 and then I send you guys through this one. Okay. So this is the solenoid control room. These guys over here, they're in 24-hour shift. They take care of everything that's related with this big solenoid superconducting magnet. I'm gonna have to repeat this like 10 times. You might as well bet it. Right, so here they essentially take care of whatever is the solenoid, just keeping the solenoid cool and having it with all the energies. And so I'm going to ask you guys to go through here, straight. You can look, when you go on your left, look at all the computers, the 1U computers. Okay. Don't touch anything.
And wait at the red door? Wait at the red door? Yeah. Yep. This is just one.
You work here?
In the summers, yeah. This is just one spot. This isn't even the main computer lab.
Are these all GNU/Linux boxes?
There's Linux. There's other things too. But mostly, yeah.
That's it. Nobody else.
That's everyone.
Okay. So this is the CDF control room. Currently it's being operated by 3 persons. This is the CO, this is what we call an ace, and this is what we call the psycho. Not because he's a crazy guy, but because he's the scientific coordinator. And I think we have a little, just in case we have a hat. He's the boss, so he yells. So you want to say something about operations in here? No. Okay, so essentially, in the past, we used to have things a little different. We used to have all the high voltage of all the sub-detectors in here for controlling this ball. And we used to have a person in here that takes care just of high voltage. You know, making sure the silicon has the high voltage, making sure the solenoid, making sure, sorry, not solenoid, the drift chamber has the high voltage. The calorimeters are okay. That used to be like that. And then in here we have the cameras that look at the actual detector. This is the real detector. You can play with the cameras but you have nothing to do. It's very fun. The part of and here we have the fire alarms, we have the total current draw of the solenoid, about 4600 amps. We have the status of the Tevatron in here. Right now it's running with protons only, it doesn't have any anti-protons in it. And then the person in here takes care of the data acquisition. Essentially, you power it up there and you look at data in here. So this machine, this little state machine in here drives the whole operation of the detector. And he's also looking, because now we decided to change things, we decided to go from our operation with a person in there and concentrate all the activities from that person to this poor guy. And he had now to do all the same things the other guy used to do before. He's now taking care of all the DAQ operations and he's taking care of all the high voltages as well. And in addition, he's monitoring the Tevatron. He's looking at the losses right now. These are the proton losses that you see in there. That means how many protons are going actually out of the orbit instead of being perfectly in a beam. So if that's too high, then we do some detectors start tripping, like the silicon, for example. And that little monitor over here I forgot to mention, so I'm gonna do it now. Each little green thing in there is one ladder of the silicon, like you saw downstairs, and it's telling us that that particular ladder is full. So you can see how many ladders we have in there, a whole lot. And then this thing over here, going back to DAQ. When you went downstairs, you saw all these computers in the farms downstairs. Back then, 2 years ago, I would say, maybe 3 years ago, we had that all in the 3rd floor, and each one was a computer this size, and full desktop. And we we had them in shelf, one by one. Now we use everything 1U, very small computers that were in the first floor. And each dot in there, each blue dot you see in there, represents one computer processing one event. And yes, when we are taking data, which is not the case now, when we have collisions between protons and protons, right now they are only passing protons. How much is it? Final proton. So they are injecting at this point the protons into the beam. They don't have, the machinists only has some number of protons. They are putting all the protons they need. Later on they're going to put all the antiprotons, and then they're going to make them collide. That's one alarm.
Gas alarm.
It's a gas alarm. So in particular, that one is taken care by the cryo downstairs, the guy you saw in the control room downstairs. And the alarms is the best thing we have. Not this particular one, but all the other ones. There's a very sexy voice saying, but there are some other ones that are very scary, like a big cow mooing, very loud. And finally, the person over here essentially looks at the data quality. He's looking at the data that comes. He was downstairs. So the person over here is looking at the quality of data. He's messing. He's checking that, you know, you may have the high voltage on, you may have everything working here perfectly, but you may not get any really good data. Maybe you see no data for one particular piece of the detector. That tells you something's wrong. So that's his job. Typically, when we're running, all these things are powered with different things, monitoring the different quantities. So let's move over here for a second.
Gas alarm. Gas alarm.
So this is what we call one of the trigger rooms. Essentially, what we do in here is we decide what events, what collisions we want to record. We say, oh, this is an interesting one because this one fired, this had a huge amount of energy deposited in here, it has this number of tracks, this looks like an interesting event. The decision is being taken here. All these electronics in here is essentially running, just making that decision. Because we cannot possibly save all the events we have, right? We have way too many. And the most we can record is about 200 per second. 50 per second. And that's the best we can do.